All right, hello everyone, and welcome back to this, the penultimate talk in this little astronomy series. So last week we talked about the beginning of the universe. This week we're going to talk about the mysterious end of the universe, as well as some mysterious concepts, dark matter and dark energy. This can get a little, first of all, it'll be really interesting at first, but then as we talk about the fate of the universe, it might get a little depressing. Hopefully it won't get too depressing though. Tonight's quote is by Terry Pratchett. Death stood alone, watching the wheat dance in the wind. Of course, it was only a metaphor. People were more than corn. They whirled through tiny, crowded lives, driven literally by clockwork, filling their days from edge to edge with the sheer effort of living. And all lives were exactly the same length, even the very long and very short ones, from the point of view of eternity, anyway. So if you were to go out on the street and you happen to run into an astronomer, one of the questions you might ask them is, what is the universe made out of? And the best answer that we have is, well, we don't really know. That might seem sort of incredible to you, especially since we've spent these last, 25 weeks talking about how we know things about distant objects. And we do know that galaxies, the gas in the galaxies, the stars in those galaxies are made out of hydrogen and helium with a smattering of heavier elements. And we can tell their chemical composition by looking at their spectra. But notice the words chemical composition. When we use those words, we're talking about the composition of material made out of atoms like hydrogen, helium, carbon, and iron. And it is true that for all of the familiar objects, the planets, the stars, the galaxies, you and I, we are made up of atoms. But that same statement might not be true for the universe as a whole. We've found through our investigations, especially over the past century, that a large portion of the universe is made out of some invisible matter, some invisible mass called dark matter, and some invisible energy called dark energy. Let's briefly introduce those two. We'll spend most of our time tonight talking about dark matter, because although we know very little about it, we know significantly more about it than we do about dark energy. And dark matter is the invisible something that we ascribe to holding galaxies together and holding galaxy clusters together. Because we found that it's not the gas that is doing that gravitational work. Instead, it's dark matter, the invisible something, this invisible mass that is doing that work. Dark energy is sort of the opposite of dark matter. Dark matter holds things together. Dark energy pushes things apart. We've noticed in the past, 5 decades or so, that the universe's expansion is not slowing down, but is instead accelerating. And there's some invisible something doing the work, different from dark matter. So we call it dark energy. So let's talk about dark matter for most of the time here tonight. So let's talk about the evidence that we have for dark matter, and then we'll get into what it actually could be. So we saw in previous weeks how the sun's motion around the galaxy reveals the total amount of mass within its orbit. And we can use the motion of stars that are further out in our galaxy to get a mass of the Milky Way within that star's orbit. And so in principle, we could determine the complete distribution of mass in the Milky Way by doing the same thing with the orbits of stars at every distance from the galactic center. Now, in practice, interstellar dust obscures our view and makes it a bit harder, but we can still use radio waves that penetrate this dust to look at atomic hydrogen clouds that radiate in the radio. And that's how we can get a good idea of what their orbital speeds might be to give us a mass. And so let's kind of summarize that kind of idea with looking at these plots that plots the orbital speed of objects against their orbital distances. So as a simple example, let's say you wanted to measure how fast kids will go around a merry-go-round. Now, the entire ride goes around the center in the same amount of time. In other words, it's not like the kids closer to the center of the ride are going at a different speed. Are completing one revolution in a different amount of time than the kids on the outside of the ride. They're all having to go around at the same amount of time. But to compensate for that, kids further from the center have to move a bit faster to cover a larger distance in the same amount of time. They've got to go a bit further to keep that same time. So if you were to plot the orbital speeds of kids on a merry-go-round, you would get this nice straight line where, for instance, a kid a meter out from the center is moving at about 2 meters per second. Meanwhile, a kid 5 meters out, this is apparently a very big merry-go-round, is moving at maybe 8 meters per second. So you get this nice straight line for any kind of solid body system. In contrast, orbital speeds in the solar system decrease with distance, since pretty much all of the mass in the solar system is concentrated in the sun. So that's why Mercury orbits much faster at almost 50 kilometers per second. Meanwhile, Neptune, all the way out at 30 astronomical units, is moving very, very, very slowly because all the mass is concentrated towards the sun. But in stark contrast to these two examples, this solar system example is sort of what we would have expected for the galaxy. We would expect that all the mass is going to be concentrated in the center, and the stars that are further out from the galactic center are going to be moving slower, just like Neptune is moving slower than Mercury. But when we do those observations that I talked about, by looking at hydrogen clouds, looking at gas clouds, and looking at stars in their orbits, we get this. It looks like that the stars in the Milky Way remain approximately constant. They're going at the same orbital velocity beyond the inner few thousand light years, beyond once you stop this rising pattern, then everyone's going pretty constant. That means that most of the mass must not be concentrated at the center. Instead, the orbits of progressively more distant gas clouds must encircle more and more mass. The sun's orbit, which I've marked here, encompasses about 100 billion solar masses. But a circle twice as large surrounds twice as much mass, and a larger circle surrounds even larger mass. So to summarize, orbital speeds in the Milky Way imply that most of our galaxy's mass lies well beyond the orbit of the sun. And a more detailed analysis would tell you that this mass is distributed throughout this spherical halo surrounding the disk of the galaxy. So when we talked about the components of our galaxy a few weeks ago, we talked about how we have the luminous disk, where all the stars do their nice, nearly circular orbits. We have the central bulge, or a bar in our case. And then we have a stellar halo, where the globular clusters hang out, where other stars that go on random orbits hang out. But I have to now add that adjective, stellar halo, because we have a dark matter halo that is significantly larger than the galaxy, than the stellar halo itself. The dark matter halo contains 10 times the total mass of all of the stars in the disk of our galaxy. So if we're interpreting this evidence correctly, then the luminous part of the Milky Way's disk is more like just the tip of the iceberg, marking only the center of a much larger clump of mass. Now you might think, what the hell is happening with the Milky Way? Is something special about us? Well, we can go look at other spiral galaxies, and we can actually determine the amount of dark matter in a galaxy by comparing a galaxy's mass to its luminosity, this is called the mass to light ratio. So here's how we calculate this stuff. So first, we use the galaxy's luminosity to estimate the amount of mass that the galaxy contains in stars. So for example, if a galaxy has 100 billion solar luminosities, if it's 100 billion times brighter than the sun, then we might say, very roughly, that it has about 100 billion solar masses in it. It has 100 billion times the mass of the sun. Then, that's just a little conversion. Then we've got to determine the galaxy's total mass by looking at the orbital speeds of stars and gas clouds in a galaxy, because those orbital speeds are responding directly to the amount of gravity interior to their orbits, the amount of mass interior to their orbits. And it's a different, conversion between taking luminosity and converting it to mass and looking at orbital velocities and converting it to mass. And when we do this, if that total mass from those orbital velocities is larger than the mass we can attribute to the stars, then that excess matter must be dark matter. So here's a table of different objects, different types of objects, and their mass to light ratios. We typically talk about mass to light ratios in solar masses per solar luminosities. So the sun has a mass to light ratio of 1, because we got 1 solar mass divided by 1 solar luminosity. Easy. Rigel, a blue supergiant, it's one of the stars in Orion, has a very, very small mass to light ratio. It's only 20 times the mass of the sun, but 120,000 times the brightness of the sun. Proxima Centauri, the closest star to us and a red dwarf, has a mass to light ratio of 70. The Pleiades and Messier 13 are both star clusters. They have a relatively small mass to light ratios. And the last 3 are galaxies. The Milky Way is a barred spiral galaxy. We think it has a mass to light ratio of 125. That means that the amount of mass in the Milky Way outweighs the light by about 125 times. Messier 87, one of the largest ellipticals near us, one of the largest galaxies near us, has a mass to light ratio of 90. So when we get around 100, that's when we think that it's being dominated by dark matter. The Large Magellanic Cloud, one of the satellites of the Milky Way, in a regular galaxy, has a very small mass to light ratio. It's probably not sitting in a huge dark matter halo, maybe just a smaller one. That is actually something cosmologists think a lot about. So we can get an idea of the amount of dark matter. And just like we made in other galaxies, and just like we made a rotation curve for the Milky Way, we can make rotation curves for other spirals. This is one that one of my professors here at Case and his team have done, where they have taken existing data and made rotation curves for tons and tons of spiral galaxies. And you can see here, first of all, they're colored by brightness, where red is the brightest, purple is the dimmest. You see orbital speeds on the vertical and distance from the center of that particular galaxy on the horizontal. You see that, some of them are screaming upwards, but eventually they all start to plateau. And in fact, it's been a running theme that every time someone says, hey, this spiral galaxy's rotation curve doesn't plateau, if you just go out and get more data at an even greater distance, eventually it does plateau. So this seems to be a trend for all spiral galaxies. So just like the Milky Way, most other spirals also have orbital speeds that remain very large at large distances. They remain high at very large distances, indicating that they also contain a large amount of dark matter. When it comes to other types of galaxies, the other major type is ellipticals. We've got to use a different technique for ellipticals. Excuse me. Because they don't have that well-organized disk in which we can see how a star's orbital velocity depends on distance. Because ellipticals will have stars going every which way. It doesn't necessarily, we can't do the same method there. Instead, we've got to rely on the spectral lines of an elliptical galaxy being Doppler broadened and shifted. So remember, if something is blue shifted, it's moving towards us. If something is red shifted, it's moving away from us. So a rotating galaxy, one part should be blue shifted, the other part should be slightly red shifted. And then it might also be broadened. The greater the broadening, the faster the stars are moving. So a wide line indicates that stars are moving fast relative to one another. Get even wider, it gets faster and faster and faster. And as we look at elliptical galaxies, importantly, we see that the same thing is happening to ellipticals. The speeds remain fairly constant as we move outwards from the center. So ellipticals contain dark matter too. So we've got these measurements suggest that elliptical galaxies, like spirals, contain 10 or more times as much mass in dark matter as they do in the form of stars. So everywhere we look, the galaxies that we see are completely dominated in mass by dark matter. It's kind of weird. We've got to explain that. What is this dark matter? Before we get to that, we can even look at galaxy clusters. In fact, this is what Swiss-American astronomer Fritz Zwicky was doing in 1933. He was looking at the Coma cluster, which is about 300 million light years away. And he was trying to calculate their cluster mass by observing galaxy motions and applying Newton's laws. Now, this guy, Fritz Zwicky, before I get into what he did, he was a great guy. He was very smart, came up with a lot of things before that ended up being true before his contemporaries were willing to accept them. He's an eccentric guy. He called people he didn't like spherical bastards because, quote, they're a bastard no matter which way you look at them. He's very cool. A great guy. Zwicky wanted to calculate the cluster mass, the total mass of all the galaxies in the Coma cluster by looking at galaxy motions and applying Newton's laws. So armed with a spectrograph, Zwicky measured the redshifts of the galaxies in a particular cluster and used these redshifts to calculate the speeds at which the individual galaxies are moving away from us. That is, the recession speed of the cluster as a whole. The speed at which the expansion of the universe carries it away from us. And he did that by averaging the speeds of its individual galaxies. And once he knew the recession speed for the cluster, Zwicky could subtract this speed from each individual galaxy speed to determine the speeds of galaxies relative to the cluster center. Of course, this method only told him the average radial component, the speed toward or away from us of the actual galaxy velocities, but by averaging over enough individual galaxies, Zwicky could get a good average orbital velocity for the cluster's galaxies as a whole. Once he knew the average orbital velocity of the galaxies, he could use Newton's universal law of gravitation to estimate the cluster's mass. And finally, he compared the cluster's mass to its luminosity. Zwicky calculated a mass of 3 quadrillion times the mass of our sun and a luminosity of 5 trillion times the luminosity of our sun, giving the Coma cluster a mass to light ratio of 600. This means he concluded that most of the matter in these clusters were not stars, but instead dark, which was much to the disbelief of many astronomers. In fact, it was actually Zwicky who coined the term dark matter. Many astronomers of his time kind of disregarded his results, believing that he must have done something wrong to arrive at these numbers. But eventually, more sophisticated measurements did prove Zwicky right. And now you can do the same math on not just the Coma cluster, but any cluster of galaxies, and you get similar numbers popping out. Huge mass to light ratios indicating that a large portion of the matter in the cluster is dark matter. And we can do this with multiple ways. So if you do it the way Zwicky did it by looking at galaxy orbits, you can look at the hot gas in a cluster. So this relies on observing X-rays from the hot gas between the galaxies. And for large clusters, this hot gas can represent 7 times as much mass as found in stars. So it's very important to take this hot gas into account. Now, you can see here 6 clusters in both visible and in X-ray light. The purple and blue are the X-ray gas. And this hot gas can tell us about dark matter because the temperature depends on the total mass of the cluster. The gas in most clusters is nearly in a state of gravitational equilibrium. That is, the outward gas pressure balances gravity's inward pull, just like inside of a star, where we got the outward pressure caused by fusion balance the inward crush of gravity. And so in this state of balance, the average kinetic energies of the particles, of the gas particles, are determined primarily by the strength of gravity and hence by the amount of mass within the cluster. And because the temperature of the gas reflects the average kinetic energies of its particles, the gas temperatures we measure with X-ray telescopes tell us the average speeds of the X-ray emitting particles. And then we can then use those particle speeds to determine the total cluster mass. Even after accounting for the hot gas in the cluster, we still see that dark matter is at least 40 times the combined mass of the galaxies in the cluster. In other words, the gravity of dark matter seems to be binding the galaxies of the cluster together in much the same way gravity helps bind matter within individual galaxies. And these two methods, looking at orbits and looking at the hot X-ray gas, work really well, but you might have noticed these basically just use Newton's laws. And we have discussed this, the successor to Newton's laws in general relativity. And so you might wonder, is this just a quirk with Newton's laws that we keep finding this unknown mass, or does general relativity also back up these predictions? And as you probably guessed, general relativity does back up the observations of dark matter. So massive objects like galaxy clusters act as gravitational lenses that bend light that passes by as predicted by general relativity. And because of the light bending angle of a gravitational lens of a cluster depends on the mass of that object, we can measure masses by observing how strongly they bend light. So for example, here, these four arrows, I pointed out what has been termed the sunburst arc galaxy. Those three arrows pointing out these weirdly curved lines here. There's three here and then another one just behind this nearby Milky Way star. That is the same, that's four images of the same galaxy that happens to be behind this cluster of galaxies situated in the center of the image. And light has taken different paths to go around this cluster. And so we see four images around the cluster. And so using general relativity, we do get the same result as Newton's laws. That galaxy clusters hold a significant amount of dark matter. So not only do individual galaxies hold dark matter, but galaxy clusters are also hotbeds for dark matter. So hopefully I've made a strong case that dark matter does exist. But is it possible that there's a completely separate explanation for these observations? So essentially all of our evidence for dark matter rests on our understanding of gravity. So one of these two statements must be true. Either dark matter really exists and we are observing the effects of its gravitational attraction, or there is something wrong with our understanding of gravity that is causing us to mistakenly infer the existence of dark matter. Now, I will say most of the astronomical community believes number one, our way of describing gravity is pretty solid. Something must change on these bigger scales with gravity to cause number two to be true. That is not saying that there's anything wrong if there's an astronomer who believes that number two is true. One of my professors here at Case is a firm believer in modified Newtonian dynamics. Let's change the way we talk about gravity just a little bit. And it does explain away many of the things that we see that we attribute to the existence of dark matter. Most of the astronomical community does not believe that. But at some point, when you're able to make predictions and the observations match your predictions, you've got to believe that. You've got to believe that there might be something up with gravity. So, but for our purposes tonight, we will say that number one is correct, that dark matter really exists and we are actually observing the effects of its gravitational attraction. I'll leave it to you go look up modified Newtonian dynamics and see what you think. So that poses the question of what is dark matter made out of? And so there are two basic possibilities. First, it could be made out of ordinary matter, what astronomers call baryonic matter. But in this case, it would be in forms too dark for us to detect with current technology. Or it could consist of one or more types of exotic matter, what astronomers call non-baryonic matter, that's completely different from atoms and does not interact with light at all. Because remember, we call it dark matter because we can't see it. It's not emitting any light. It's not even reflecting light. It's doing nothing with light. So it might be exotic matter, or it might be just really, really, really dark, ordinary matter. But to determine which one of these two possibilities it is, first, we need to calculate how much dark matter is out there. When discussing the matter content of the universe, astronomers usually talk about densities. They take the amount of some matter in a large volume of space to determine the average density of that matter. Then those densities are stated in terms of the critical density, and that is the density of mass energy needed to make the universe flat. What they get out of this is something like this. So the top pie chart is the percentage of matter in the universe. How much of it is dark matter, how much of it is normal matter. Most of the matter in the universe, most of the mass in the universe is dark matter, about 84% of it. The bottom pie chart shows you the mass energy budget in the universe. So adding up all the energy and all the mass, since those two can be exchanged, E equals mc squared, remember that. Then the stars, the planets, the galaxies, you and I, we are just 5% of the stuff in the universe. Dark matter makes up about 26% of it. And then the mysterious dark energy is almost 70% of it. So we know how much dark matter there is. We know how much total matter that is. And now we got to see which of these two basic possibilities can give us these, can match these numbers. So we look at the possibility that it could be ordinary matter. Basically, if an object is too dim to be seen in the galactic halo or beyond, then it qualifies as a dark matter candidate. So that means planets, brown dwarfs, those kind of failed stars, brown dwarfs, and even some faint red dwarfs, some faint red main sequence stars qualify as dark matter. Neutron stars, black holes, white dwarfs. If we can't see them in the galactic halo, if they're too far away, then it could be a dark matter candidate. However, and there's actually a word for this type of object. They're called machos, massively compact halo objects, machos. However, the Big Bang Theory does allow us to place limits on the amount of ordinary matter in the universe. So remember from last week, during that era of nucleosynthesis, where the entire universe was hot enough for fusion to happen everywhere. Remember that protons and neutrons were going to fuse together to form deuterium, hydrogen with a proton, neutron, and the nucleus. And all of that deuterium was then fused with another proton to make helium. And so some of that deuterium still exists. And the amount of deuterium that's still around tells us about the density of protons and neutrons in the early universe. And those calculations and observations tell us that the density of ordinary matter is around 5%, not enough to make it dark matter. Here you can see our observations and predictions. So on the vertical, we've got the number of particles relative to hydrogen. For helium in the green line, helium-4 in the green line, deuterium in the red, helium-3 in the dark blue, and lithium-7 in this kind of ugly purple color. And then on the top horizontal, we've got the fraction of critical density. So what percentage makes up the matter? And you can see our predictions are in these big boxes. Deuterium tightly constrains things. And look, our observations match exactly with our predictions that it's going to be around 4 to 5% of the of the critical density of the universe. Lithium is a problem. We're still working on lithium, but all our observations indicate that ordinary matter there's not enough of it in the universe to make up dark matter. So our macho theory that dark matter could be planets we can't see, black holes we can't see, it's been tossed out for a few years now. Now, when it comes to exotic matter, that's the more likely explanation for what dark matter is. So remember that neutrinos are dark by nature. Remember what neutrinos are. Those are those incredibly lightweight particles that are produced a lot in nuclear fusion. We encountered it when we talked about the fusion in the sun. Neutrinos are dark by nature because they don't have electrical charge and thus can't interact with light. They are never bound together with charged particles in the way that neutrons are bound together in atomic nuclei. So their presence can't even be revealed by associated light-emitting particles. And they only interact with other forms of matter through gravity and the weak nuclear force. And for this reason, we call them weakly interacting particles. Now, dark matter can't be neutrinos because neutrinos travel at nearly the speed of light. They are incredibly massless, incredibly lightweight, I should say. And so they can't be bound to a galaxy as dark matter. But maybe, just maybe there are heavier versions, and we call these weakly interacting massive particles, or WIMPs. They could make up most of the mass of a galaxy or cluster and still be completely invisible. So basically, if we get a really heavy neutrino or something like that, that still doesn't interact via electromagnetism, doesn't emit light, doesn't reflect light, and only interacts via gravity and the weak nuclear force, or maybe some more exotic force yet to be discovered, then WIMPs could be dark matter. WIMPs would also not be able to collapse into a disk either. Remember, we've got a dark matter halo, not a dark matter disk. We've got a dark matter halo. And the only reason the stars and dust and gas collapsed to a disk is because they lost orbital energy by radiating away light. WIMPs would not interact with light, so they couldn't collapse, and as they collapse, lose their energy by radiating it away through light. They'd still be stuck in far-out orbits in the galactic halo and around halos in other galaxies. So WIMPs are the leading hypothesis for what dark matter is. Now, obviously, we got a prediction. Let's see if we can have observations to back up this prediction. Well, we could detect WIMPs with 3 methods. First of all, we've got indirect detection. Maybe 2 WIMPs interacting with each other. Maybe they don't interact with normal matter, maybe they interact with each other. Maybe that interaction would produce ordinary matter in the form of gamma rays or neutrinos, which would be detectable. Maybe we can produce WIMPs inside particle accelerators like at CERN in Geneva by smashing ordinary matter together. Maybe if we just throw matter together at high enough speeds and energies, they'll just produce some dark matter, produce some WIMPs. Maybe we can directly detect them. Maybe some WIMPs will pass through detectors here on Earth, bouncing off of atoms via the weak nuclear force, very similar to how we detect neutrinos on Earth. In all 3 of these cases, as of yet, not a dang thing has been credibly confirmed. So WIMPs, as originally expected, have been thoroughly falsified. So what do we have left? I don't know. It's a big mystery. We don't really know what dark matter could actually be. This last statement that WIMPs have been thoroughly falsified and we don't really have any other explanation leads people like my professor to work on modified gravity. Other people are still pushing the bounds of research and trying to look everywhere for WIMPs. I've looked, it's like looking for your keys and you can't find them. You've checked the tables, you've checked, on top of counters and whatnot. Haven't looked everywhere. Have you looked underneath the rug? Have you looked, in the dog's bed? I mean, that's essentially what people are doing now. Checked all the obvious places. Let's look for the weird places. So you don't really know what dark matter is yet. But we do know that dark matter plays a huge role in our universe. It does play a role in galaxy formation and galaxy cluster formation. So remember that stars, galaxies, and clusters of galaxies are gravitationally bound systems, meaning that their gravity is strong enough to hold them together against the expansion of the universe. Galaxies in clusters probably form normally. It's like any isolated galaxy. We talked about the formation of galaxies a few times already. And eventually, that dark matter associated with the entire cluster most likely reversed the galaxy's expansion with the universe and pulled them back in so that galaxies fell back inward and began orbiting each other. When we look out at different clusters, some clusters aren't finished forming. The nearby Virgo cluster is actually tugging on the Milky Way and the local group. And the local group may eventually merge with the Virgo cluster. So here is sort of not a rotation diagram, but a Hubble diagram where we've got recessional velocity, how fast are they moving away from us, the distance from us in millions of light years, mega light years. All the small black points are some of the brighter galaxies in the Virgo cluster. This dark black line is Hubble's law, what their recessional velocity should be based on their distance. The blue square is the prediction, the average of the average distance for the Virgo cluster. Throw it into Hubble's law, we should get that recessional velocity, maybe about 1,200 kilometers per second. The red circle is the average of their recessional speeds, and it's about maybe 900 kilometers per second. So that difference there is called the Virgo-centric flow, that we are actually moving towards the Virgo cluster. And as we look on even larger scales, galaxy clusters are tugging on each other, hinting that they might be part of larger gravitationally bound systems called superclusters. So for example, here is our local group. We've got the Milky Way down here at the bottom right, and its host of satellite galaxies, the large and small Magellanica Cloud, some other dwarfs. We've got the Andromeda Galaxy and its host of satellite galaxies, the Triangulum. It has a few satellites, some other smaller galaxies in the local group. Our local group is just a small part of an even bigger system called the Laniakea, Hawaiian for immense heavens. That is a huge collection of clusters. So you saw where our local group is. Virgo cluster is over here. Beyond the Virgo is the Centaurus. So we've got these kind of arms coming off of this. This is the Laniakea supercluster. Clearly, the gravity of dark matter is having a large influence on the structure of the universe. And beyond about 300 million light years from Earth, deviations from Hubble's law, owing to gravitational tugs, just like what happens between us and the Virgo cluster, are insignificant compared with the universal expansion. So Hubble's law becomes our primary method of getting distances out here. Using this law, astronomers can make maps of the distribution of galaxies in space, and we can reveal some large-scale structures vaster than the clusters of galaxies. So here are a compendium of two different large-scale structure surveys shown in these little wedges. So the first wedge on the left, the Milky Way is at the vertex. It's all the way here at the far left. And this first wedge is from the Smithsonian Center for Astrophysics survey, which extended about 600 million light years from Earth. You can see these large structures, these large walls. Here it's pointing out the CFA Great Wall, and then voids between those walls where there's comparatively few galaxies. Then these other two wedges are from the Sloan Digital Sky Survey, and this first wedge extends to about 1.2 billion light years, and that third wedge extends to about 2.5 billion light years. And we can still see some large-scale structures. Here's this big one called the Sloan Great Wall. It's about 1 billion light years long. And as we get further out, the distributions of galaxies becomes way more uniformly distributed. And so we see two things here. We see that galaxies are not scattered randomly throughout space, but are arranged in chains and sheets separated by voids. And on larger scales, galaxies do appear uniformly distributed, which is in agreement with the cosmological principle. Now, why do we see walls and voids and chains and all that kind of stuff? Well, all these large-scale structures probably started out as just mildly high density regions of different sizes, while the voids sort of started as mildly low density regions. And so according to this model, the structures that we see should mirror the original distribution of dark matter in the early universe. And according to this model of structure formation, we can use supercomputer models to simulate the growth of galaxies, clusters, and larger structures from just density enhancements as the universe evolves. And models of extremely large regions reveal how dark matter should be distributed throughout the entire universe. And the results of those models look remarkably similar to those slices of the universe. So here's a very well-known one called the Millennium Simulation. We're looking at sort of a galaxy cluster, and we do see walls and darker areas, voids. This is dark matter. None of this is light or ordinary matter. This is how dark matter is. It's distributed in this simulation. And it looks pretty dang similar to the actual observations. So overall, we now seem to have a basic picture of how galaxies and large-scale structures formed in the universe, perhaps starting from quantum fluctuations that occurred when the universe was a tiny fraction of a second old. And so over these past few weeks, we have seen that the large-scale development of the universe to date has been governed by these two competing processes. The ongoing expansion that began with the Big Bang, which tends to drive galaxies apart from one another, and the gravitational attraction of matter in the universe, which assembles galaxies and larger scale structures around the density enhancements that emerged from the Big Bang. And these ideas naturally lead us to one of the ultimate questions in astronomy. How will the universe end? After Edwin Hubble discovered the expansion of the universe, astronomers generally assumed that the end would be kind of in fire. If gravity were strong enough, the expansion would someday halt and reverse. The universe would then begin collapsing and heating back up, eventually ending in a fiery and cataclysmic crunch. Alternatively, if the total strength of gravity were too weak, gravity would never slow the expansion enough for it to halt and reverse, leading to an icy end in which the universe would grow ever colder as galaxies moved ever farther apart. Much to astronomers' surprise, nearly 2 decades of observations now show that the expansion is not slowing at all, but instead is accelerating with time. As we've discussed, this implies the existence of some repulsive force produced by a mysterious form of energy we have come to call dark energy. So to understand evidence that has led astronomers to conclude that the expansion is accelerating, let's consider 4 different expansion models for the universe. And over at the right, you'll see kind of diagrams for that. So the first model is a recollapsing universe where gravity is strong enough. There's maybe enough matter in the universe for gravity to be strong enough, and maybe there's no repulsion in this universe, that the expansion will eventually slow down and reverse. We call this scenario the big crunch, as opposed to the Big Bang. Maybe we live in a critical universe where there's a weak gravitational attraction and no repulsion. And that expansion is just going to continually decelerate forever, leading to a universe that would never collapse, but would expand ever more slowly as time progressed. We call it a critical universe because calculations show that it is what we would expect if the total density of the universe were the critical density and only matter and not dark energy contributed to that. We also have a coasting universe where, once again, a very weak gravitational attraction and no repulsive force, the expansion might just continue on at the current rate, where no forces are acting to speed it up or slow it down. And then we have the accelerating universe, where there's a repulsive force strong enough to overcome gravity. That expansion will accelerate, causing galaxies to recede from one another with ever-increasing speed. Note that each of these models leads to a different age for the universe today. In all four models, the size of a particular region of space and the expansion rate of the universe are the same for the present, because those values must agree with our measurements for the average distance between galaxies today and for the Hubble's constant today. However, the four models extend to different lengths into the past. You can see that here, where each of these four models, we've got the recollapsing, the big crunch in red, the critical in green, the coasting in blue, and the accelerating in yellow. And they each give you a different age in the past. For a recollapsing, the universe is still relatively young. And then progressively older as we get towards the accelerating universe. So observing galaxies further in the past to see what their average distances between galaxies were further in the past can actually help us support or reject these predictions. And so using data from the early universe with white dwarf supernovae as the distance calibrators, I mentioned that because if something is wrong with those distance calibrators, then these measurements will be wrong. The data shown here in these gray points with these small error bars clearly fit the accelerating model the best. And the discovery of an accelerating expansion, which was discovered only 2 decades ago in 1998, was met with immense shock by the astronomy community. But 3 of the team leaders, Saul Perlmutter, Brian Schmidt, and Adam Rice, were awarded the 2011 Nobel Prize in Physics for that discovery. So the acceleration of the expansion of the universe clearly implies the existence of some force that acts to push galaxies apart. And the source of this force has been dark energy, But keep in mind that as little as we know about dark matter, we know even less about dark energy. None of the 4 known forces in nature could provide a force strong enough to overcome gravity. And while some theories of fundamental physics suggest ways in which energy could fit the bill, no known type of energy produces the right amount of acceleration. What we do know is that matter makes up about 30% of the matter energy budget of the universe. And measurements indicate that dark energy makes up about 70% of that budget. The model that includes dark energy gives a prediction for the age of the universe at about 13.8 billion years, which is in good agreement with what we infer from Hubble's constant and the ages of the oldest stars. But what that dark energy is, we have literally no idea. And so we're now ready to return to the question of the fate of the universe. The recollapsing universe is only one of our 4 possible expansion models that has an end in fire, and the data don't fit that model. Therefore, it seems the universe is doomed to expand forever, its galaxies receding ever more quickly into an icy, empty future. So what will happen in the distant future if the universe continues expanding forever? We can use our current understanding of physics to hypothesize about the answer. So first, the answer obviously depends on how much the expansion of the universe accelerates in the future. Some scientists speculate that the repulsive force due to dark energy might strengthen with time. In that case, perhaps in a few tens of billions of years, the growing repulsive force would tear apart our galaxy, our solar system, and even matter itself in a catastrophic event sometimes called the Big Rip. However, evidence for this type of growing repulsion is very, very weak, and it seems more likely that the expansion will continue to accelerate more gradually. We call this a big freeze. And so if the universe continues to expand in this way, galaxies and galaxy clusters will remain gravitationally bound far into the future. However, galaxies will not always look the same because that star-gas-star cycle cannot continue forever. With each generation of stars, more mass becomes locked up in planets, brown dwarfs, white dwarfs, neutron stars, and black holes. Eventually, about 1 trillion years from now, even the longest-lived stars will burn out, and the galaxies will fade into darkness. At this point, the only new action in the universe will occur on the rare occasion when 2 objects, such as 2 brown dwarfs or 2 white dwarfs, collide within a galaxy. The vast distances separating star systems and galaxies make such collisions extremely rare. So for example, the probability of our sun, or the white dwarf that it will become, colliding with another star is so small that it would be expected to happen only once in a quadrillion years. However, given a long enough period of time, even low probability events will eventually happen many times. So if a star system experiences a collision once in a quadrillion years, it will experience about 100 collisions in 100 quadrillion years. By the time the universe reaches an age of 10 to the 20 years, star systems will have suffered an average of 100,000 collisions each, making a time-lapse history of any galaxy look like a cosmic game of billiards. These multiple collisions will severely disrupt galaxies. As an anti-gravitational encounter, some objects lose energy in such collisions and some gain energy. Objects that gain enough energy will be flung into intergalactic space to be carried away from their home galaxies with the expansion of the universe. Objects that lose energy will eventually fall to the galactic center, leaving behind a single supermassive black hole where the galaxy used to be. The remains of the universe will consist of widely separated black holes with masses as great as 1 trillion solar masses and widely scattered planets, brown dwarfs, and stellar corpses. If Earth somehow survives, it will be a frozen chunk of rock in the darkness of the expanding universe, billions of light years away from any other solid object. If grand unified theories are correct, Earth still cannot last forever. These theories predict that protons will eventually fall apart. The predicted lifetime of protons is extremely long, a half-life of at least 10 to the 33 years. However, if protons really do decay, then by the time the universe is 10 to the 40 years old, Earth and all other atomic matter will have disintegrated into radiation and subatomic particles. And the final phase may come through a mechanism proposed by the physicist Stephen Hawking. Recall that he predicted that black holes must eventually evaporate, turning their mass energy into Hawking radiation. The process is so slow that we do not expect to be able to see it from any existing black holes. But if it really occurs, then black holes in the far distant future will disappear in brilliant bursts of radiation. The largest black holes will last the longest, but even trillion solar mass black holes will evaporate sometime after the universe reaches an age of 10 to the 100 years. From then on, the universe will consist only of individual photons and subatomic particles, each separated by enormous distances from the others. Nothing new will ever happen, and no events will ever occur that would allow an omniscient observer to distinguish past from future. In a sense, the universe will have finally reached the end of time. Now, lest any of this sound depressing, and it might sound depressing to you, keep in mind that we are talking about incredibly long times. Remember that 10 to the 11 years is already nearly 10 times the age of the current universe. 10 to the 12 years is another 10 times that, and so on. So a time of 10 to the 100 years is so long that we can barely even describe it. But one way to think about it, thanks to the late Carl Sagan, is to imagine that if you wanted to write on a piece of paper a number that consisted of a 1 followed by 10 to the 100 zeros, it sounds easy, but a piece of paper large enough to hold all those zeros would not fit in the observable universe today. That still does not alleviate your concerns. You may be glad to know that a few creative thinkers are already speculating about ways in which the universe might avoid an icy fate or undergo rebirth even after the end of time. Perhaps of greater significance, speculating about the future of the universe means speculating about forever. And forever leaves us with a very long time in which to make new discoveries. After all, it is only in the past century that we learned that we live in an expanding universe, and only in the past couple of decades that we were surprised to learn that the expansion is accelerating. The universe may yet hold other surprises that might force us to rethink what might happen between now and the end of time. So that is the end of the penultimate talk. Next week will be the final one of this series, where we'll kind of look back on everything that we've talked about. We'll do a little poetic waxing, and we'll bring it all together. So as always, for the second to last time, like, comment, subscribe, leave questions down below if you have any of them, and I'd be happy to answer them. But without further ado, I will see you all next week.